Okay. Thanks to the organisers for giving me a chance to speak here today. This is my title. Okay, let's begin. So in string theory, if we want to relate to low energy physics, we need to compactify, and to compactify we need to stabilize moduli. So in type 2b string theory, you can do this on flux compactifications. However, in the context of heterotic string theory, it's a bit more difficult because you only have NS and S flux present. And in particular, there's a theorem by Strominger that says that on heterotic compactification, if you have maximal symmetry and non-vanishing H flux, you can't have a Calabi-Yau compactification. So for a Calabi-Yau case, H flux has to be 0. So to proceed, we look at the mirror dual of H3. And this is a manifold with SU3 structure, which means that while there's a spinor that leaves a quarter of the supersymmetry charges unbroken, in this non-Calabi-Yau case, the covariant derivative with respect to the Levi-Civita connection is proportional to some torsion. Yeah, so basically there are two ways to go about satisfying this theorem. One is to move away from Calabi-Yau and look at SU3 structure manifolds, and this has been done for the case of so-called half-flat manifolds. Or you can break maximal symmetry of D equals 4 spacetime. So in this case, there's work has been done in half BPS domain walls, in which 2 of the 4 SUSY generators in D equals 4 n equals 1 are unbroken. And there's Poincare symmetry is broken in the transverse direction. And if you look at the SU3 structure fibered over this transverse direction, it looks like a 7D G2 structure. So our work is basically generalizing this to codimension 2 topological defects. So from a 10D perspective, it looks like 6 compact dimensions and 2 non-compact dimensions, which we call X and Y. And so we make an ansatz that this could be a spin 7 structure. And with the spin 7 structure, there's an invariant 4 form, which you can decompose under the 6D SU3 structure forms, J and omega, which reduce to the usual closed forms in the Calabi-Yau case. And if we look at the 10D supersymmetry transformations, this gives some flow equations in dj and d omega in terms of the H flux and phi hat, which is the 10D dilaton. And now we want to match this to this 10D ansatz to an ansatz for the 4D theory. So since there's one unbroken supercharge in the singlet of spin 7, we assume that we take a guess that this could be a quarter BPS solution in 4D. So we make a quarter BPS ansatz for the killing spinners and get some killing spinner equation of the form shown on the screen. And here the A's correspond to the axiodilaton, as well as the Kähler moduli and complex structure moduli. So basically, in this paper, we matched these 10D flow equations to the 4D quarter BPS killing spinner equations, and basically we find that the d omega equation matches to the Kähler moduli in 4D, dj goes to complex structure moduli, and the remaining equation with the other condition goes to the dilaton equation. And in particular, the axion that is 0 because we don't want any torsion in the 4D. So there are some applications of this which we are looking into. One is to further understand these solutions and to consider the possibility of moduli stabilization using D terms. And also looking at the so-called generalized half-flat manifolds with Gukov-Vafa-Witten superpotential. These look similar to, this superpotential looks similar to superpotentials that have been used for models of Starobinsky-like inflation. So that's another direction to consider. Okay, so that's all I wanted to say. Are there any questions? Or clarifications? Or
Okay, so the next speaker is Professor Arau.
Okay, good afternoon. My name is Ivan Arrao from Tokyo University of Science. I come to talk about extension of the Nambu-Goldstone theory, specifically for non-relativistic systems. The standard Nambu-Goldstone theory basically says that you have an action which is invariant under the group G, which is the large group. The vacuum is not necessarily invariant under the action of the full group. Instead of that, it's invariant under the action of a subgroup. And the dimension of the coset, I mean, you can define a coset space, and the dimension of the coset space defines the number of broken generators. And basically, the number of Nambu-Goldstone bosons is equal to the number of broken generators. This is the standard Nambu-Goldstone theory. And the condition of a spontaneous symmetry breaking is that one on the right-hand side. Basically, the commutator between the order parameter and the broken generator vacuum expectation value different from 0. So when you develop and introduce intermediate set of states and assume invariance under space-time translation, you can derive you can reach the conclusion that the momentum and the energy go simultaneously to 0, and you conclude that the dispersion relation has to be linear. What happened in non-relativistic system? Well, Murayama, Watanabe, and Browner, they have demonstrated that the number of Nambu-Goldstone bosons is not necessarily equal to the number of broken generators. The reason I will explain in a moment, but in principle, there are pair of broken generators canonically conjugate each other, and this condition has to be satisfied. If you expand in terms of intermediate set of complete states in the same footing as before, the same way as before, you realize that this condition is nothing else. Is saying that basically two broken generators generate one single degree of freedom. And this can be concluded after doing the same procedures as before. Finally, I propose a final condition. Basically, Nielsen and Chada in the past demonstrated that the dispersion relation for the Nambu-Goldstone bosons coming from canonically conjugate pairs have to be quadratic. I have realized that the conditions of Nielsen and Chada can be summarized in this statement. Basically, the commutator of the commutator. The second commutator is the matrix rho, which Murayama, Watanabe, and Browner demonstrated. In my case, I extended the spontaneous symmetry Riemann condition for including the order parameter. When you develop fully the same, you introduce intermediate set of complete states, and you do the spatial integrations and assume translational invariance on the space-time, space-time translational invariance for the charges. You reach to the conclusion that when you concentrate in the neighborhood when the momentum goes to 0, you reach to the conclusion that in fact the dispersion relation has to be quadratic. And this is the relation found by Murayama, Watanabe, and Browner. The number of broken generators minus the number of Nambu-Goldstone bosons is equal 1/2 the rank of the matrix rho. The matrix rho is defined in this way by the commutator of the canonically conjugate pairs of broken generators. Finally, at the space-time level, it's in development, but I can say that the way how I analyzing is how the different observers define the vacuum at different positions for the space-time. Two observers defining the same equivalent space-time equivalent vacuums, they can be connected through asymmetry directly. But two observers defining inequivalent vacuums, they are connected through broken generators. Basically, there are many formulations of gravity which suggest that this should be correct. Still, I have time, so I can reach the conclusions. The conclusions is, in non-relativistic systems, the Nambu-Goldstone theory is satisfied if we take into account the correction of the dimension of the coset space. What does it mean? It means that the expressions found by Murayama and colleagues is equivalent to a correction of the dimension of the coset space if you look at it closer. In some sense, is equivalent to think that part of the canonically conjugate operators become order parameters. The correction of the dimension of the coset space is directly connected with the dispersion relation corrections, as I demonstrated before. The intersection of the three conditions, namely the standard spontaneous symmetry condition, the expression found by Murayama and colleagues, and the expression proposed by me, the intersection of these three conditions gives you the appropriate dispersion relation and the appropriate number of Nambu-Goldstone bosons in non-relativistic system. But this is for internal symmetries. For space-time symmetries, it's in process. Thank you very much. That's all. Okay.
The next speaker is Professor Hua.
So my aim in the next 5 minutes is to define a general fermionic SPT phase. This is part of a joint work with Gaetan and Kapustin. Consider 2 plus 1 dimensional TFT with a topological boundary condition. To this system we can attach the data of a spherical fusion category. The objects on this category are line defects living on the boundary, and I will denote them like this. The morphisms are local operators living between lines, and I will denote them either like this or like this. We can fuse the local operators along the line, and this gives rise to composition of morphisms. Reversing the orientation of a line gives rise to the dual object. Fusing the lines together gives rise to the notion of tensor product on the category. And placing the lines in a certain fashion gives rise to an canonical associator, evaluation, and a co-evaluation map. Assembling all these ingredients together, we can assign a number to any graph drawn on a sphere. To do this, first remove a point to obtain a planar graph, and then read the graph from bottom to top. So here we have an identity line coming in, which breaks apart into A and A dual using the co-evaluation map for A. Then A goes into B and C using the morphism M1, and so on. Ultimately, you see that this graph just defines a morphism from identity line to itself, so which is just a number. And this number is invariant in the topological manipulations of the graph drawn on the sphere. Physically, this computes the partition function of the theory on living inside this ball with this network of line defects inserted on the boundary. In fact, we can glue together many of these balls to construct the partition function of the theory on any free manifold. This is known as the Torai-Viro construction. So we see that a spherical fusion category completely characterizes a TFT. We can also include bulk lines in this formalism. So bringing a bulk line to the boundary, I denote a bulk line by a double line. Bringing it to the boundary gives rise to a half braiding with every boundary line. Bringing it to the boundary in different ways is equivalent. So we can move the bulk lines across morphisms. This is just the defining data of the Drinfeld center of the spherical fusion category. The existence of a Z2 one-form symmetry is a statement about the existence of a special bulk line with the following properties. Here, plus sign corresponds to the non-anomalous case, and minus sign corresponds to the anomalous one. Now, the main physical idea is that we can construct a spin TFT from an ordinary TFT with an anomalous Z2 one-form symmetry. To do this, consider this ordinary TFT, combine it with the TFT generated in the IR from a single free massive fermion. This system has a non-anomalous Z2 one-form symmetry, which we can gauge to obtain the spin TFT we want. This idea can be used to define a fermionic SPT phase, as they are supposed to flow to spin TFTs in the infrared. So I will now define SPT phases in terms of spherical fusion categories. In general, if a TFT has global symmetry G, then the spherical fusion category splits apart into subcategories graded by the group elements. A bosonic SPT phase has a single simple element in each of these subcategories, such that the simple objects give rise to fuse together to give simple objects. It is completely characterized by a group 3 cocycle coming from the associator, which can be computed from a diagram like this. Now I will define fermionic SPT phases, first described by Gu and Mem. To do this, consider central extension G hat of G by Z2. Then consider a bosonic SPT phase protected by G hat and gauge the Z2 subgroup inside it. This gives rise to a category which has two simple objects. And the fusion rules are completely characterized by a group 2 cocycle. Demanding that the system has an anomalous Z2 conform symmetry constrains the G hat associator in terms of a G group supercohomology element given by mu 3 and n2. Graphically, this is just the following statement, where this graph defines mu 3 for us. Now, to define a general fermionic SPT phase, we still need one more ingredient, which is the Ising category. This is a Z2 graded category, which has two simple objects in the trivial grade and one simple object in the non-trivial grade. There are some fusion rules, and there are some non-trivial associators. We choose a generator for the anomalous Z2 conform symmetry, and I call the spin TFT generated like this as I. To define a general fermionic SPT phase, consider a homomorphism pi1 from G to Z2. Now pull back icing along it. This gives us a category in which there are two simple objects with G maps to 0. So ultimately the fermionic aspirative phase is given by product of Gouvain and icing pullback.
Next speaker is Dongmin Gang.
So I'm Dong Gang from Kabuli IPMU. So my talk is about the space of 3D n equal to CFT. So the minimal 3D n equal to CFT, which has small center charge, is known to be the critical Sumina model. And the natural question we can ask is what is the next simplest CFT and what is the next simplest CFT. So this case is very interesting but very challenging. So in this talk, I will focus on certain subclass of 3D n equal to system and ask the same question to this subclass. So we are considering in this talk I'm considering the 3D CFT which obtained by left empire brain. We start from the 60 2,an minus 2,0 theory and we do some computation on the inter-3 manifold M with some topology twisting which preserves the cutoff VPS. And then the resulting 3D IR system will be described as 3D N2 system which has the labeled by N and the inter-3 manifold M. So we are interested in the simple series, so we pick the N equal 2, and then the 3D series is labeled by the internal 3 manifold. And if we choose two simple 3 manifold, then the resulting IR theory will be trivial. And if we choose two complicated 3 manifold, then the resulting 3D CFT will have the complicated theory which has higher the large central charge. So one topological invariant which makes the complexity of the internal 3 manifold called the hyperbolic volume, and which can be thought as some 3D analogy of the Euler characteristic in 2D Riemann surface. And I didn't mention here, but at the large end, we can do the computation of central charge exactly at the large end using holography, and we can check that the central charge at the large end is linearly proportional to the hyperbolic volume. So for non-hyperbolic case, we expect that the resulting 3D CFT is trivial theory, and so for hyperbolic cases, the mathematician found that the spectrum of the hyperbolic volume for smooth 3 manifold, and there is a lower bound which is saturated by the Wick's manifold, and the spectrum is discrete, and and as we increase the volume, then the density will become higher, then there is infinite number of the hyperbolic volume with a certain value, critical values. So goal of our project is to compute the central charge of 3D CFT correspond to this small 3 manifold, and we expect it will give the small central charge, and check with the Wick's manifold to give the minimal central charge and what is the value of central charge. So here is our basic strategy to compute the central charge of left empire brain system. First, for n equal 2 system, this central charge is related to some quotient Partition function, quotient 3 sphere partition function, which is parameter by quotient parameter B. And then this quotient 3 sphere partition function, using the so-called 3D square correspondence, is related to some SL2C complex consignment theory on the internal 3 manifold. So then we will use some state integral. We develop a state integral model to compute this free energy for the closed 3 manifold, and we compute the central charge. So this is a very simple example of this computation of central charge. First of the example is the Wick's manifold, which is known to have the smallest hypervolume, which can be realized some dense energy on the 3 sphere with some link called heightened link with this one. So from this expression, we can write down the Partition function as an overlap of two wave functions. One corresponds to solid torus and one corresponds to this not complement. Solid torus is very simple, so we can easily write down this state integral model with some proper choice of position basis, and this can be given by this one. Next thing, the notable thing is that we should compute the wave function for the not link complement, but there is a developed tool by the student developer using the ideal triangulation of this not complement. So combining this technique, we can write down the full expression for the Partition function of the Wick's manifold this way. And we did some concept check using the two alternative prescription of the 3 manifold of M003. One is using by including solid torus along some heightened link component. Another is ideal tetrahedron. Two expressions give a total independent one. different expression, but we check that the box distribution is the same asymptotic expansion, at least more B. So we can write down the Hudson function for the Weeks manifold in this way, and we check that possibility that we expect it will give the asymptotic expansion for B, and this has an exact symmetry. So we expect that if we do the integration of this formal integration along some conversion cycle we can choose, then we can give the exact homological value. So this is a summary, and we are planning to compute this one, but unfortunately we couldn't finish this numerical evaluation, and so we cannot give the precise number, but I hope that we can report this numerical value soon.
Next speaker is Professor Nick Houston.
Hello. So, my name is Nick. I'm a postdoc just down the road from here. Well, broadly speaking, so this is a talk about supersymmetric and BPS solutions in supergravity, which obviously are the special configurations that preserve some amount of the underlying supersymmetry and so are therefore interesting for various reasons. Now, obviously this is a topic that's been extensively studied, but what's particularly interesting is that the space of solutions that are known is almost completely unexplored in one particular direction, which is when the fermions are non-trivial. Now, setting the gravitino, for example, to 0 is convenient, but it's not necessarily the full picture. So, building on some work that I did earlier this year, I'm going to be asking what happens when you switch the fermions on. So, obviously, the starting point is the usual supersymmetry condition, which asserts the existence of Killing spinors. Now, when you switch the fermions on, there's a new term in the connection, K, which comes from the fact that typically you have space-time torsion. Now, for various reasons, it makes sense to equate this with the gravitino. For one thing, it allows psi to rotate into itself under supersymmetry, and also because d epsilon is always a solution of the equations of motion, no matter how non-trivial it is. Now, what's particularly important here is the fact that even though epsilon doesn't look like a Killing spinor anymore, it still provides all the Killing vectors of the underlying geometry. So this means the bosonic symmetries are preserved. Now this happens in this precise instance because K corresponds to the torsion. And for example, the symmetry of Killing's equation removes exactly the torsionful piece of the connection. This is a specific example of a more general phenomenon where the bosonic fields don't feel the effect of the torsion. So as I said, the symmetries are preserved. So demonstrating that the bosonic fields are invariant isn't too difficult in practice. Now, I'm simplifying a bit. You still have to satisfy this relation, which is effectively the equation of motion for the torsion, so you have to engineer things a little bit. And when you do that, typically what happens is that some of the delta psi's vanish and some don't, which is what you would expect from a BPS state. Okay, so since the torsion might be relatively unfamiliar, it may be useful to make some remarks. Torsion in English refers to the twisting that something possesses, and in this context it's the twisting of inertial frames under parallel transport. Now that's kind of an interesting thing to think about, but it's not really clear how we should kind of interpret that in the context of other aspects of space-time geometry. So sometimes it's useful to, just take a particle physics perspective. As far as the Poincare group is concerned, the mass and the spin are equally fundamental quantities, and of course it's one that leads to the curvature and the other that leads to the torsion. We know mass tells spacetime how to curve, spacetime tells mass how to move, thanks to John Wheeler. So we can make an analogous observation in the present context, that spin tells spacetime how to twist, and spacetime tells spin how to precess. You don't need to be afraid of torsion. Okay, so maybe it's useful to have an example. So the gravitino is the gauge field of local supersymmetry, which suggests that just as in Yang-Mills theory and general relativity, there should be some solutions which look like instantons. Now the thing is, if you look in the torsion-free limit, you won't be able to find them. But if you allow the possibility of torsion, and you sort of follow the rubric that was set out 2 slides ago, you can find these solutions in a relatively straightforward manner. In order to preserve the BPS saturation, you find that you need K to be self-dual, or anti-self-dual, which is obviously sensible in this context. The way that you engineer this in practice is by using a self-dual Yang-Mills connection, also known as an instanton. Eta here is the self-dual Toft symbol. So if you compute, for example, the usual topological invariance, you find you get chi for the background, which is the Euler number of the background manifold, plus mod k. K is the instanton number for the instanton you chose, plus all the other usual properties you would expect, zero action, half BPS, pure gauge infinity, and so on. And by doing things in this way, okay, you can repurpose the usual Yang-Mills technology into supergravity. So you can use the ADHM method and the various generalizations thereof to find all possible solutions. Okay, so some conclusions in future work. The take-home message is don't fear fermions. Okay. Some things to look at: uses of these instanton solutions, possible generalizations to monopoles, black holes that have some non-trivial fermionic aspect, exotic FBS states. I don't really have time to explain that, but if you want to know, you can come and ask me, and you can read all about it in this, and hopefully soon this. Thank you.
Next speaker is Professor Surbi Chapel.
Hi, I'm Surbi Khetrapal and I will speak on universal corrections to entanglement entropy of local quantum quenches. This talk is based on this paper with Justin David and Prem Kumar. In a field theory with an entanglement interval L1 to L2, consider an excited state at origin at 0 time. Under time evolution, this excited state propagates along the light cone. As the excited state encounters the entanglement interval, it is expected that the entanglement entropy of the interval will change. The change is given by a step function. Here, in this entropy versus time plot, the black dashed line shows the step function, which has a non-zero value for time between L1 and L2. This is the change in entropy when the width of the excited state is 0. When the excited state has non-zero width, the change in entropy is given by the blue curve. So the step function becomes smooth. The profile of the smoothing depends on the details of the CFT. However, we show that the correction to this Renyian entanglement entropies at order epsilon square, that is at second order in the width of this excited state, the correction is universal. It has a universal time dependence. So for this, we evaluate the nth Rene entropy of the entanglement interval in the presence of the excited state. It is given as a function of the trace of n powers of the reduced density matrix of the excited state, where the density matrix of the excited state is given here. It is obtained by acting on the thermal density matrix with O and O dagger operators and then evolving in time. On the uniformized plane, the locations of the operators are at x1 and x4 minus I epsilon and I epsilon, and x2 to x3 is the location of the entanglement interval. This quantity, the trace rho NA, is actually a 2 endpoint function on an n-sheeted Riemann surface. So to evaluate it, we use a uniformization map and go from the n-sheeted Riemann surface to a uniformized plane, where each sheet of the n-sheeted Riemann surface is mapped to a slice on this uniformized plane, this slice. And these are the locations of the operators on the uniformized plane. So essentially, the problem of calculating a 2 endpoint function on an n-sheeted Riemann surface, it reduces to a problem of evaluating a 2 endpoint function on a plane. Here is the result. So the change in nth Rene entropy at leading order in epsilon is a step function, and we find that the subleading correction happens at order epsilon square, and it is given by this function of time, and it is proportional to the conformal dimension of the excited state operator. And we show that the time dependence of the correction at this order is universal. To evaluate this, this 2 endpoint function of these operators on the n-sheeted Riemann surface is evaluated by considering the OPE expansion of 2 operators on one sheet. We consider theories where the dimension of the lowest line primary is greater than 1. In this case, the stress tensor is the first subleading term in the OPE expansion, and so the correction at order epsilon square in the 2 endpoint function as well as the correction to the Rayleigh entropy at order epsilon square is just given by the expectation value of the stress tensor on an n-sheeted Riemann surface, and hence the time dependence of the correction at this order is universal. We have done several checks. This result matches with the second Rayleigh entropy of the phi 2-1 operator of a p prime minimal model, where the exact result in epsilon is known. We have also got agreement with the order epsilon square correction to holographic entanglement entropy. We have looked at the large interval late time limit. In this limit, the expectation value of the stress tensor on an n-sheeted Riemann surface, it just reduces to the expectation value of the stress tensor on a cylinder of period n beta. So this is independently obtained result, and it matches with the large interval late time limit of the result I showed in the previous slides. And finally, we have also looked at this excited state on a CFT which is deformed by the chemical potential for higher spin currents. And in this case, the leading correction happens at order epsilon square mu square, and it is given by the 3-point function of the stress tensor with 2 higher spin currents. Thank you.
Our next speaker is Professor Mikhail Premchuk.
So my talk is based on our work in which we describe thermalization in the boundary theory by looking at the dynamics of point particles. Sorry? Does it work? Okay. So my talk is based on the description of thermalization in the boundary theory by looking at the dynamics of point particles in the bulk. The basic idea is that the formation of the black hole in the bulk should holographically correspond to the process of thermalization of the boundary. And one of the ways to create a black hole is to collide some particles. Our goal is holographic diagnostic of BTZ black hole formation by a collision of point particles in the 3-dimensional ADS, and to probe the boundary dual to this ADS3 spacetime with colliding particles, which supposedly should thermalize. We calculate 2-point correlation functions and see if they somehow in agreement with the thermal correlation functions due to the BTZ background. So in this talk I focus on the case of colliding massless particles. Here in the left picture the movement of a massless particle in the ADS3 is represented as a cartoon of constant time sections of the ADS3 cylinder. The particle cuts out a wedge out of the space-time, and its faces are identified. So we deal with defects, global defects in ADS3. So on the right-hand side, the picture of colliding particle is presented. So how the actual collision happens? At time -π/2, particles start from antipodal points from the boundary and move towards each other head-on. The collision happens at the moment t equals 0. And if the particle energy is high enough, higher than this threshold, then the black hole is formed with a mass defined by this relation. But before that, at some point during the movement of particles towards each other, the apparent horizon forms at this moment of time. We calculate 2-point correlation functions in the boundary theory of light scalar operator by using geodesic approximation, in which we have to sum over all geodesics between 2 given boundary points. Since we have defects in the bulk, we have to deal with winding geodesics. We have to take into account winding geodesics as well as a direct geodesic. So to do that, we use a geodesic image method developed in our previous work, which the basic idea is that the length of a winding geodesic equals to the length of a geodesic to a point which is obtained by acting with the identification isometry on the original point. And we also imply the holographic renormalization scheme which takes into account this identification. So here I show some results. Here we plot the inverse equal time correlation function as a function of angular separation. The blue line is a correlator dual to the background with colliding particles, and the red line is a correlator dual to the BTZ background. So this first plot is when particles start moving, so there is no agreement. but when they move at some time moment, particles, the apparent horizon appears. So this immediately reflects on the correlation function. And when the time flows further, these 2 points, which are defined by the horizon sizes of their respective bulk spacetimes, move towards the origin, and correlators start to have good agreement. So conclusions. We see that collisions of point particles in ADS3 allow to construct explicit dynamical model of thermalization of boundary theory. And we see also that the winding geodesics are essential in the description of thermodynamics in and out of equilibrium in the boundary dual of ADS3. And since the size of area of apparent horizon is smaller than the BTC horizon area, we also conclude that we can conclude that UV degrees of freedom thermalized before than infrared degrees of freedom. We also have some directions for future study, namely to make precise contact with other models, calculations, and we also think that we can reproduce the proposed model of thermalization from the CFT computation. And we also need to investigate the role of non-perturbative semi-classical corrections to the geodesic approximation during the thermalization process. Thank you for your attention.
Our next speaker, Professor Kuharski. Start.
Hello, I will tell you about BPS invariance from extremal A polynomials, and this talk is based on my works with Piotr Sulkowski and Stavros Gorfalidis. Main object of our interest are Labastida-Marinho-Oguri-Vafa invariants, and NRIJ, which are an open version of Gopakuma-Vafa invariants. NRIJ count the number of BPS states arising from M2 branes ending on M5, embedded in resolved conifold. NRIJ are given by home-flippity polynomials colored by representations of SUN. Each P is a polynomial of A describing the size of the conifold and Q being the exponent of topological string coupling. Unfortunately, the dependence is complicated and nonlinear, so values of NRJ were known only for representations with small number of boxes. But we noticed that LMOV invariants and home-flippity polynomials for symmetric representations and extremal powers of A form a closed subsystem, which we can see on the example of small r equals 3. This equation works for both maximal and minimal A power, and so do others in the rest of the talk. There will be one exception marked explicitly. Closure of this subsystem enabled a qualitative change. We could use extremal A polynomials and connect LMOV invariants to the different branch of knot theory. Quantum A polynomials encode recursions for home-flippity polynomials for symmetric representations, which can be written as operator A annihilating P. And this equation in classical limit, Q going to 1, reduces to extremal A polynomial, A of x and y. The solution of A equals 0 encodes classical LMOV invariant in the following way. BR equals to all NRJs for the same representation R. Solving the classical equation, A equals 0, we managed to find explicit formulas for classical LMOV invariants. Here we can see one for the figure 8 knot. Mu is the Möbius function. Note that physically based integrality of LMOV invariants combined with R squared in the denominator implies non-trivial number theory predictions. We proved this integrality for a wide class of knots and observed that the product of BR and the knot-dependent integer gamma is divisible by R, and this improved integrality is even stronger than M-theory predictions. Our quantum results are based on the recursion relation for home-flippity polynomials. We found the combinatorial model for constructing LMOV invariants. This set contains objects corresponding to an 2J for the trefoil knot. and j corresponds to the number of boxes, which is 2, 4, and so on. Moreover, for wide class of nodes, we proved integrality of LMOV invariants and found the explicit recursion relation for nRj. Summing up, LMOV invariants, which count BPS states, are expressed by Hom-Flippity polynomials, which we can see on the old example. However, for symmetric representations and minimal or maximal powers of A, we can use quantum and classical A polynomials. Solutions of A equals 0 encode BR in this product formula. This equation and its quantum analog give us the access to explicit values, recursion relations, combinatorial models, and integrality properties of LMOV invariants. Thank you for attention.
Next speaker is Professor Chun Nian. Let's start.
Okay. Okay, first I would like to thank the organizers for giving me the opportunity to speak here. And today I'm going to talk about some relation between string theory and Bose-Einstein condensates. And this talk is based on my joint work with my collaborators, and some papers published, and the others will come up soon. So we all know that string theory has many applications. For instance, we can apply string theory technique, ADS-CFT, to like a strongly coupled system. And there are many applications to cosmology. But my personal point of view is a little conservative. So I would like to find a real system, a quantum system of strings, and apply and test the ideas and results of string theory in this system, which is available at current technology. And it turns out that Bose-Einstein condensates is a good candidate because the basic ingredients in string theory, open string, closed string, difference, and some others. And we have similar configurations in Bose-Einstein condensates, which are vertex lines, vertex rings, and solitons. The question is, can we make this correspondence more rigorous? And the answer is yes. Because the effective theory to describe Bose-Einstein condensates is gross PDSV theory. And it turns out that we can map this theory to effective string theory. And this idea was initiated by Z in the 90s and then recently revisited by Gapser, Naya, and Parrott. We can start from this Lagrangian and apply this parametrization. It's just a very simple Lagrangian for complex scalar, and we rewrite the Lagrangian into this form. The crucial term is this one, which is a derivative acting on the face of the complex scalar. And we can separate the face into smooth part and the singular part. If we partially integrate this smooth part, we get partial mu acting on f mu equals 0 and can be solved. And the solution is f mu just the field strength of a two form. And the two form turns out to be the b mu nu in the string theory, effective string theory action. And the other, the singular part gives us non-trivial topology, which is gives us actually the position of the string, or the vertex line, or the string in the effective theory. So you can see after some steps, we arrived at this effective theory, which is basically the string theory, but without a string tension term, or can be viewed as string theory in the large B field limit, plus additional field strength term. And in the previous work, they only consider closed string. And we want to go one step further to introduce open string. to make the identification of open string with open vertex line BC. So there are two key new ideas, new ingredients. One is we consider the dark soliton solution as a boundary spacetime. The second ingredient is previous people have done the 3+1 duality, and we found the two forms being new. And because we have the boundary, we can do 2+1 duality on the boundary, then we get one form. And then we just get this string theory action. It's a standard string theory action in the presence of the deep-brain with additional field strength term. And it's a gauge invariant. And we use the non-commutative geometry to test the idea, and we can identify the soliton solution as the soliton in the commutative Tachyon field theory, and the deep-brain is a soliton solution in effective string theory, and the non-commutative soliton is identified with deep-brain based on the previous work. Due to lack of time, I just show you some numerics. So this is deep-brain, or the dark soliton. This is vertex line. So it's a realization of BIO. And we also study the decay of this configuration.
Our next speaker is Professor Tom Gutierrez. Let's start now.
Thank you very much for the invitation. My name is Tom Rodelius, and I'll be talking about the classification of little string theories. This talk is based on a couple of papers with various collaborators, and the interested viewer should also see the talks by Mina and Kamran on related issues. So if you were at Strings 2015, you heard a couple of my collaborators and I discuss the classification of 6D superconformal field theories. And the result is that 6D SCFTs all take the very simple form of these generalized quivers. So in this diagram, these blue circles indicate tensor multiplets, which are paired with gauge groups. And they're connected by these black lines, which represent bifundamental hypermultiplets and more complicated configurations of matter called conformal matter. The quivers are very simple. There's some decoration allowed on the far left and the far right, but the interior is completely fixed, and there are no loops. The classification looks like chemistry. We begin with atoms, which are clusters of tensor multiplets in gauge groups that do not have matter, which allows them to be Higgs. And we join these together via conformal matter to form more complicated radicals and molecules, which are themselves 6D SCFTs. Now, I want to do the same thing and classify little string theories. Before I even tell you what a little string theory is, let me tell you why you should care. Little string theories are non-gravitational string theories, and in this sense, they serve as a toy model for the full string theory. They sit between 6D SCFTs and supergravity theories in 6 dimensions in a way that I'll make more precise shortly. And so the hope is that we can understand these theories better by understanding little string theories. There are 3 things I want you to remember from my talk. The first one is simply the definition of little string theory. Little string theories are UV-complete, non-local theories in 6 dimensions with gravity decoupled and an intrinsic string scale. And they're characterized by the presence of a non-dynamical tensor multiplet. This tensor multiplet has a scalar field in it, and the web of this scalar is what sets this intrinsic string scale. Secondly, 6-dimensional theories have strings which are charged under some collection of 2 forms. The associated string charge lattice has a Dirac pairing similar to the ordinary Dirac pairing in 4 dimensions. For a 6D SCFT, this Dirac pairing has only positive eigenvalues. For a 6D supergravity theory, it has 1 negative eigenvalue and the rest are positive. And for a little string theory, it has 1 null eigenvalue and the rest are positive. This is the sense in which a little string theory sits between a 6D SCFT and a 6D supergravity theory. Finally, the main point of my talk is that once we have the classification of 6D SCFTs, which I discussed at the beginning, we get the classification of little string theories almost for free. That's because every little string theory can be thought of as the affinization of a 6D SCFT, whereby we take the SCFT quiver, we add a single tensor node, which will give us a non-dynamical tensor multiplet, and we get an LST. For example, we can consider the 2,0 theories. These admit an ADE classification, and the quiver diagram for the SCFTs is simply the AD and E type Dinkin diagram. To move from the SCFT to the LST, all we have to do is add a single node to the quiver, and thereby getting the affine Dinkin diagram. So here you should take the word affinization quite literally. As a more non-trivial example, we can consider this 1,0 theory. We start with the 6D SCFT, we add a single tensor node here at the end, and now we have an LST. So to recap, LSTs are 6-dimensional theories with gravity decoupled, a non-dynamical tensor, and an intrinsic string scale. Their Dirac pairing is positive semi-definite with exactly one null eigenvalue, and the classification of 6D SCFTs enables the classification of little string theories by this process of affinization. Thank you. Are there any quick questions? Okay. Oh, they're telling me that time is up. They're telling me that time is up.
Yeah, sorry, the next speaker.
We can talk in private.
Okay, I want to report on a work in progress in a collaboration with...
Next speaker is Professor.
Yes.
Let's start.
Okay, I want to talk about, I want to report on a kind of work in progress in a collaboration with Sebastian Campos, me, and Kumo Basta. When we first started this project, we wanted to study and construct a large class of 2D 0,2 theories, which we took to be small volume theories of D1 branes probing a toric-Calabi-Yau fourfold. By realizing these theories in terms of branes, we wanted to analyze the dynamics of these 2D theories, as well as identify a brane realization of a new correspondence of 2D theories that is now known as Gadek-Bukov-Putov triality. When you T-dualize these D1 branes, you obtain D4 branes suspended between NS5 branes that drop a holomorphic surface sigma. This new type 2A brane configuration we call as a brane break model. This holomorphic surface sigma comes from the toric-Calabi-Yau fourfold, which is characterized by its toric diagram and Newton polynomial fourfold. So for C4, you have this toric diagram corresponding Newton polynomial. The D4 and NS5 branes meet at planes that wrap free torus inside this holomorphic surface sigma. These planes form a polytope on T3, which we call as a brane break. Faces of this brane break correspond to either chiral or Fermi multiplets of our 2D 0,2 theory. The punchline here is that the boundary of this brane break is a representation of the NS5 branes wrapping the holomorphic surface sigma, and the interior of this brane break is a representation of the D4 branes suspended between the NS5 branes. These are brane breaks, so in the case of C4 is a truncated octahedron, stacked next to each other to truncate, to tessellate a free torus. If I pick a Fermi multiplet, it's represented by a square in the brane break model, whose one-dimensional boundary is a representation of the J and E term interactions in the 2D Lagrangian. If we have also a cubic brane break, we can do a local deformation of the brane break model, which translates to Gadek-Bukov-Putov triality of the 2D 0,2 theory corresponding to this brane break model. So that we can show in terms of this brane break model corresponding to the cone over the Q111 over Z2 surface, which contains a cubic brane break that rotates 3 times until it comes to the original brane break model under triality. A natural description of brane break models is also in terms of the mirror picture given by coming from the toric geometry. The mirror can be thought of as a direct vibration over a plane W, where at the origin of the W plane, the S1 vibration shrinks, and at critical points of the W plane, the complex surface sigma coming from the Newton polynomial pinches. So it contains an S2 at this point, which degenerates. The topology over this line, over this interval on the W plane can be thought of as a S4. And each of these S4s correspond to a gauge group in the 2D theory, and also correspond to a brane break in our brane break picture. We have multiple such S4s on which the 5 branes wrap in the mirror picture. These S4s all come together at the origin of the W plane and intersect. And the graph that describes the intersections of these S4s is precisely related to the brane break picture I was showing you before. So let me summarize. We have the 5 branes wrapping 4 cycles, which gives rise to a brane break model corresponding to a 2D 0,2 theory, living on a D1 brane probing a Calabi-Yau 4-fold. In the past, people have also studied the 6 branes wrapping 3 cycles, which corresponds to an object called the diamond model, or brane tiling, that describes a 4-dimensional theory living on a D3 brane probing a Calabi-Yau 3-fold. In terms of the mirror picture, there is a natural generalization or sequence of this analogy. One can also think about Euclidean D4 branes wrapping 5 cycles that describe what we call a brane hyperbolic model that corresponds to a 0-dimensional matrix model that lives on a D-1 brane probing a Calabi-Yau 5-fold. In fact, these critical points on the W plane and the cycles they can move into each other, forming dualities between theories. So we want to talk about this later. Thank you.
Next speaker is Kai Vincent. Start now.
Good afternoon. I'm going to talk about some recent progress on the quantization of the mirror curve of toric Calabi-Yau. This is a joint work with Min-Xin Huang and Xin Wang. Xin Wang has presented it in the poster session. The non-public computation of topological string theory has drawn much attention in recent years due to its various dual facets. Topological string may have many different non-public definitions. For example, using the localization in conformal field theory, Locker and Waffa proposed a non-public partition function of refined topological string. Other relations with matrix models, APGM series, and quantum integral systems all shed some light on this issue. The quantization of the mirror curve of local Calabi-Yau has turned out to be an excellent testing ground to study the non-public effect of topological string. The local Calabi-Yau are the surfaces with anti-canonical line bundle. Its mirror is effectively a curve. This Vi is the vector in the toric diagram. For example, for local P2, we want to study such a quantum mechanical system. In general, there are two quantization approaches. One originated from the base sketch correspondence proposed by Nekrasov Shatashvili in 2009. Via geometrical engineering, this supersymmetric vacuum equation or base ansatz can be rephrased in the context of topological string. The exact NS quantization condition for the mirror curve was obtained last year. It contains 3 parts: the polynomial part, the perturbative instant part, and the non-perturbative part. The perturbative instant part and the non-perturbative part are closely related to the instant Nekrasov-Shatashvili free energy, but with a crucial B field added. This quantization condition contains no poles and enjoy a self-S duality. It also can be derived from the Locker-Waffa partition function of topological string. Another approach is proposed by Marino and the collaborators 2 years ago. their approach takes deep root in the AVGM theory. They define the generalized grand potential. It contains two parts. One part, the WKB part, comes from the mass free energy, while the worldsheet part comes from the traditional topological string. The GHM conjecture says the generalized spectral determinant of the inverse operator of the quantum mirror curve is given by the generalized grand potential in such a way. With this grand potential, we can also define the quantum Riemann theta function in this way, and then the GHM quantization condition for the mirror curve can be written as the theta function equals 0, which means the spectra are encoded in the quantum divisor of the quantum Riemann theta function. The relation between these two approaches was rather mysterious. Our paper want to establish their relation. Our main result is that there exists a set of constant integral vectors, which we call the R field. The intersections of the theta divisors of our quantum Riemann theta function with the R field in this position coincide with the spectra determined by the NS spectra. In addition, all the R field are the representatives of B field, which means for all triples of degree and spin such that the refined BPS environment is non-vanishing, they must satisfy this relation. This is also the definition of B field. Actually, we found a set of novel identities which guarantee this equivalence. For an arbitrary toric Calabi-Yau threefold with Keller module T and the charge matrix C, we found this identity holds. This Fn refines just the traditional topological string amplitudes, and the Fns is the infrasoul charge relief energy. This is a highly non-trivial identity. It imposes infinite constraints among the refined BPS environments. We have verified this identity for many models, including the Bezier surfaces and C3 portion by Z5 auto and Z9 geometries. We also proved in some special cases.
Our next speaker is Dr. Yi Wang. Let's start.
Thank you. Before talking about the expansion history of the primordial universe, let's first review our current universe. So the expansion of our current universe has been known for 100 years, and now we are in an era of precision cosmology that we know the expansion at percent level. We know there are the standard candles like type 1a supernova, there are the standard rulers like baryonic acoustic oscillation. From all of this, we know that our universe now is dominated by dark energy, and before that is dominated by matter, and before that dominated by radiation. However, there is a horizon problem telling us that the radiation-dominated universe cannot be eternal to the past. There has to be something new in the primordial universe. For example, there could be inflation that the universe was expanding exponentially in the primordial universe. But this is not the only choice, that there could also be faster contraction, for example, the matter bound scenario, and the slow contraction, for example, the epirotic scenario, and slow expansion, for example, the string gas cosmology. For sure, inflation is the most natural paradigm, it's the best scenario. However, there are also other possibilities which are being studied. So it is nice to distinguish these scenarios observationally. And these scenarios differ from each other because of the expansion history, evolution history of the primordial universe. So it would be nice if the question is equivalent to how to measure the expansion history of the primordial universe. And it is a very difficult question. This is because there is no structure in the primordial universe. There is no type 1a supernova, there is no baryonic acoustic oscillation. The only thing existing in the primordial universe is the 10 to the minus 5 fluctuations, thin fluctuations. But fortunately, it is still possible to measure the history of the primordial universe by two ways. One way is the primordial gravitational waves, and the other is the quantum primordial standard clocks. I have no time to talk about the primordial gravitational waves, but there is disadvantage that it can only distinguish inflation between the economic scenario, but it cannot distinguish inflation between string gas cosmology, cannot distinguish inflation between the matter contraction scenario in an effective way, as the Chinese characters indicate here. And today I'm sharing with you the other scenario, the quantum primordial standard clause. The idea is very simple. From the most basic idea of quantum mechanics, that if we have a state which has definite energy, after some time evolution, the state is changed by a phase factor. Well, okay, this is the simplest quantum mechanics, so how it could be relevant to our primordial universe? And actually, we can combine this with another idea, with another thing, that we notice there exist massive fields in the primordial universe. We know they must exist. And combining these two things together, actually there is something non-trivial, that the primordial universe has a time-dependent background, and the massive fields excite massive particles from the time-dependent background. And these massive particles behave like a clock, and the clock measures the physical time much shorter than 5 minutes. So, if in the future experiment, we can measure the correlation between the massive field and the curvature perturbation, we know the correlation between the physical time and the conformal time, which is horizon crossing time of the curvature perturbation. This is, in other words, we are able to know the conformal time as a function of the physical time. In other words, we are able to know the scale factor as a function of whatever time. And in other words, we can probe the expansion history of the primordial universe, and in other words, we can distinguish inflation between matter contraction, slow expansion, and ecologic scenario by a single observer. And finally, welcome to visit us at the High Energy Group at Hong Kong University of Science and Technology. We have a nice group in a beautiful university. 面向大海，春暖花开。Thank you.
Speaker. Coming up. Our next speaker is Jie Chang Wu from Peking University. Let's start now.
First, thanks the opportunity to talk about my recent work. I will talk one-loop partition function in ADS-3CFT2, and this work is cooperated with my Professor Minton. And the recent discussion for holographic entanglement entropy draw attention to ADS-3CFT2 system, because in this case, both the gravity set and the field theory set are simplified. Most of the time, when we study the ring entropy or entanglement entropy, by replica trick, it will transform to partition function on a heterogeneous Riemann surface. By ADS-3CFT2 correspondence, the heterogeneous partition function in field theory should due to the handle-body partition function in gravity set. And the classical on-shell action in gravity should due to well anomaly in field theory, which is C21 order. And the one-loop partition function in gravity set due to C20 order partition function in conformal field theory. In gravity set, the one-loop partition function in handle-body background can be calculated by heat kernel method by this group in 2008. And in this work, we studied the C20 order partition function in two-dimensional conformal field theory, and we get the same result as in gravity set like this. Here, the Riemann surface can be realized by Schottky group, or Schottky uniformization like this, and the gamma belongs to the primary conjugate class in Schottky group. Here, Q gamma is a multiplier of gamma. In two-dimensional conformal field theory, the heterogeneous partition function can be calculated by the so-called cutting and inserting reset. For example, in this case, for a heterogeneous Riemann surface, we can cut each of the handle and insert a complete basis at each of the handle. And then the partition function transforms to a summation of multi-point correlation function like this. Most of the time, this equation is very hard to calculate. However, in large central charge limit, there are a lot of simplification. First, semi-classically, only vacuum module states dominate in the partition function, and the other module states are non-perturbatively depressed. Here we assume that this theory is a large central charge theory with sparse light spectrum. And furthermore, if you only keep leading order of 1/c expansion, there is further simplification. For example, when we consider the correlation function for multi-stress tensor, then this correlation function is captured by a summation of product of two-point function. And all the other terms are 1/c expansion. And that means in this sense, the correlation function is free for leading order of 1/c expansion. And all the three-point interaction are depressed. And the vortex operator can be written as this, as a product of stress tensor with some partial on it. And with this simplification, we can develop a diagram root to calculate the partition function. Here, in the diagram, the upper and lower dot denote a stress tensor with some partial on it. And the dashed line here denotes the summation for the M, and the solid line denotes contraction of two stress tensor. Then we can define a closed contour with solid and dashed line as a link. Each link is a product of two-point function. With this diagram language, we can classify all of the diagrams and find a one-to-one correspondence between a link and the Schottky group. Oh, okay. And with this diagram rule, we can calculate the partition function, and our results match with the gravity. And that means up to C20 order, the partition function in gravity set and field theory set match with each other. For more detail, please see my poster. And do you have any question or comment? And if no more questions, thanks for your attention.
Next speaker is Zhenbin Yang. Okay, let's start now.
All right. Thank you. I'm Zhenbin Yang. Today I'll talk about work based on Amory, Paczynski, and Juan, Douglas, and me. So the main message I want to deliver is first explain what is the conformal symmetry here and how it's breaking in ADS2. So let's look back at QADS2, where we have constant negative curvature, and in addition we have boundary metric, where I said 1 over epsilon squared, epsilon is the ADS cutoff. Note that this equation admits a set of solutions generated by large gauge transformations. Or alternatively, we can say that we can leave the metric to be ADS2 and then choose arbitrary boundary. Then by boundary diffeomorphism, we can satisfy the boundary condition. So there are solutions. Here I choose Poincare metric, and then the boundary is purely determined by one family of function, Tu, where U is the boundary time. Okay, this is also confirmed by asymptotic symmetry analysis of ADS2, which you also find one-dimensional conformal symmetry. However, pure ADS2 do not accept any dynamics. It's topological because the Einstein-Hilbert term is topological. So next, let's consider about near ADS2, which can be think of as arise from the near extremal black holes. So we have actual dimensions. The size is the dilettante field. Here we introduce the simplest model with the Jekyll-Tedbow model with 5 times r plus 2. So variation of phi gives us r plus 2 equals 0. The metric is always ADS2. And then we have Einstein equation, which is a linear equation on dilettante field, which essentially tells you dilettante is non-dynamical and has dimension -1. So let's look back at our previous modes. Now, because of the dilaton, the boundary value of the dilaton pick up unique shape, so the other shapes are no longer on shell. And we have equation for the dilaton for the boundary modes, which is determined by the boundary value of the dilaton. Then a natural question is asked, what's the effective action for those off-shell modes? The answer is by Schwarzschild derivative with coupling phi r, where the r is the renormalized dilaton boundary value. This has a few properties. First, it's local and proportional to phi r, as it should be. Second, it expands the near extremal entropy. If you do set-point evaluation, you find it's near linear in temperature. The third is it gives you the maximum chaotic behavior. This is also discussed in Douglas' talk in today's morning. Yeah. So next slide, I'll explain how to get the Schwarzschild derivative from the Jekyll-Tedder model. We just simply impose the dilaton equation. So we have a constant negative curvature background. This gives us purely boundary action, which is the extrinsic curvature. And then evaluating this extrinsic curvature on those modes gives us the Schwarzschild derivative. Okay. For the last minute, I want to explain how does the matter interact in each other with gravity if there's no change on the metric. Since we already see that the metric is always constant, always not back-reacted. So the answer is that matter excites the dilaton field, which will change the boundary shape. Or we can see excitation of the Shudu-Nambu-Goldstone modes. Say we have some ADS vacuum, and we impose some operator V at time 0, and then an operator W at time U. Without back reaction, these two particles just go through each other. But if we think about the back reaction of V, then the distribution of dilaton change. So the boundary value of dilaton pick up a different shape. Then we apply W, we got a different state. So if we initially have two particles and another particle goes through and it appears later, which is a chaperone time delay. Okay, thank you.
Consider superconformal theory in even dimensions. We can say that supersymmetric linear entropy intrinsically depends on the wire anomaly coefficients. And furthermore, if you look carefully, the different entropy objects in information theory, turns out the supersymmetric linear entropy can be interpreted as the linear divergence, which actually satisfies a set of inequalities from some mathematical consequence. So imposing these inequalities for the supersymmetric linear entropy then give the bounds for conformal field theory. These are different entropies in information theory, but in this talk we're concerned the last one, which is linear divergence, which essentially measures two distributions. The divergence between two distributions with alpha deformation parameter. So these are entropy inequalities, which actually was proved in the information theory textbook. We will show here the supersymmetric linear entropy also satisfies these inequalities. If we go to quantum systems, the analog of this probability distribution is actually density matrix, which often appears in measuring the quantum entanglement. If you're working on in this quantum field theory, one can actually define a density matrix for global state and a subregion A by tracing over these field variables in a bar. So when the global state is vacuum and A is the ball, the universal part of linear entropy, which is free of divergence, is considered to be physical and universal. By physical and universal, I mean the scheme independent. They are actually the counterparts of the quantum mechanical entropies, which, as said before, satisfy a set of inequalities. So one may ask, what are the quantum field's counterparts of the linear entropy inequalities? Actually, it can be checked. Both the free, all the available free field results and the holographic results satisfy the inequalities, but their scalings are dramatically different. I'm talking about this Rayleigh entropy at this moment. So the coupling dependence of Rayleigh entropy is not yet understood. For instance, for n=4 superior males. Rayleigh entropy does not have universal behavior for general alpha. This makes it difficult to use these inequalities. So one may twist this original Rayleigh entropy to be supersymmetric. This was first proposed by Nishioka and Yerkov in 2013. This twist is the following. As you say, the twisted Rayleigh entropy actually carry a non-trivial chemical potential in this twist formula, which was actually determined by the supersymmetric condition. The mu is equals to alpha minus 1 over alpha. So let us identify two distributions. One is the normalized energy distribution, and the other is the charge distribution. You can clearly say the supersymmetric Rayleigh entropy is nothing but the minus Rayleigh divergence. Then the following two inequalities directly follows from the inequalities satisfied by Rayleigh divergence. Here is the mathematical proof of these inequalities for the Rayleigh divergence. The first one is the monotonicity, and the other one, the second one is the concavity for this combination of alpha minus 1 times the alpha. So if you assume further the thermal entropy associated with the Replik-Trig time direction is bounded below by charge, you can actually further prove there are two more inequalities in the box, in the red box. This lower bound for this thermal entropy in this supersymmetric system can be derived from the causality condition in holography for CFTs having gravity duals, although we don't have a direct field theory proof for the lower bound of the thermal entropy yet. Let's say two examples. First of all, for n=1 and n=2, can be worked out supersymmetric Rayleigh entropy for n=1 at very small alpha is proportional to 3c minus 2a. For n=2 is completely determined by a and c. So imposing the inequalities, one can get non-trivial bound for this a over c, both for n=1 and n=2. As you can see, this is not as tight as the Hoffman-Madsen bound, so it would be interesting to imposing more entropy inequalities to get full Hoffman-Madsen bounds. The other example is 6D example. Actually, the supersymmetry Rayleigh entropy can be fully determined by this wire along A and C for the 62-0 theory, which also gives us a lower bound for this A over C, which is 3 over 7. Thank you.
Okay, so since I'm the last speaker, does that mean like I have more time? No? Okay. Okay, sorry. So, okay, I would like to give a short story of one-loop test of supersymmetric higher-spin ADS CFT. And this is based on the work, part of the work with Ipan and Ergen Seskin to appear. So, Vasiliev higher-spin theory in ADS4 has been conjectured to be due to 3D singly sectored of the free vector models on the boundary. And a non-trivial test to compare the free energy on both sides. In the bulk, we can expand the free energy at a series of g for small g. A direct computation of the leading term, f0, is hard because we don't have a Lagrangian description. But f1 is doable, the one-loop correction. And on the boundary side, so f CFT is proportional to f0 by this m, and f0 stands for a single component of the free energy. So when the subleading terms in the bulk, when they are proportional to this f0, then we can reach the following identification of the parameters with some integer number delta. Okay. So this test for type A and type B series have been conducted by these authors, Jumbi, Kolobnov, and Safdie. And it works very well for type A model, but for type B model, there's a mismatch in the free energy. And the author comments that one should first look at transimus coupled fermions. And since the fermion provides a shift in the transcendence level k, so it is not justified to simply subtract the contribution given by the transcendence term to get to the parity preserving one. We generalize the result to Constant-Vasiliev theory. Constant-Vasiliev theory contains supersymmetric Harris-Spin cases, and you know that for n greater or equal to 2, there's no shift of this transcendence level, so probably this test to work. So this is a brief review of Constant-Vasiliev series. S stands for a singleton representation in the bulk. M is the fundamental representation of some group, UM, USPM, or OM. And if we do the following products, we can arrive at these three Harris-Spin algebras. And below, these are supersymmetric Harris-Spin cases. So you see that it is necessary to have m equal to n equal to some positive integer in order to have supersymmetric cases. And we employ a method introduced by the authors to compute the bulk one-loop free energy, utilizing the character of irreducible representation of SO2, 3. And we also generalize the result to the fermionic Harris-Spin cases. The result is this. So the contributions from the fermionic Harris-Spin fields, they cancel. And for these three algebras, we have the one-loop correction of the free energy, the function of n and m. And these are the boundary free energy, F0, as I mentioned before. So in order to arrive at this match, so namely F1 proportional to F0, we need to impose a really strong constraint n should be equal to 0. And this is very strange because when n equals to 0, supersymmetric cases are ruled out. Okay, and I should remind you that this result is for boundary CFT living on S3 boundary. We also did a test for thermal ADS, namely with the boundary S1 cross S2. And in this case, the free energy, the one-loop free energy consists of three terms: F beta, beta EC, and some log divergence. Thank you. And we found that the last two terms, the Casimir energy and that log divergence, they vanish. And the only non-trivial contribution is that F beta, the thermal free energy. And these are the results for this F beta term. And they match perfectly with the boundary theories. So the conclusion that for thermal ADS case, it seems that the one-loop test suggests the duality between the Constant-Vasiliev theory and the corresponding CFTs on the boundary. But for ADS with S3 boundary, there's a really strong constraint on that n, so n should be equal to 0. So this is a puzzle, and we don't know why at this stage, and we would like to come back to this puzzle and solve it in the future. Thank you.
Okay, this concludes this session. I propose to give a quick hand to thank all our speakers.